discussion today is on velocity time graphs. A velocity time graph is a graph in which the velocity is plotted on the y-axis and time is plotted on the x-axis. Let us now discuss examples of velocity time graphs. In this topic, we are going to discuss the nature of different velocity time graphs and deduce very vital information out of such graphs. Our first graph, this is the graph that we have. We have velocity on the y-axis, time on the x-axis, and then that is the line. So we would like to know, what does this graph tell us much about? First thing that we can see is that this is a straight line and it is parallel to the x-axis or the time axis. So what important information does it tell us? One thing that it tells us is that this velocity is not changing. Therefore, we can say it is constant velocity. Another thing that we can see is that it is not zero, and therefore the body that is represented using this graph has a non-zero constant velocity. Another thing that this graph tells us is that the acceleration is zero. Whenever we have a constant velocity, it simply means that there is no change in velocity and therefore the acceleration remains to be zero. Let's look at our second graph. We have time in the x-axis, velocity on the y-axis, and then this is the line we have. One thing that we can see clearly is that this is a straight line that is sloping from bottom left to top right. So it implies that this velocity is changing, and because this is a straight line, how does it change? It is changing uniformly. So this is a non-constant velocity as the first thing. Second thing is that the velocity is increasing uniformly with time. Whenever the velocity is increasing uniformly with time, it simply tells us that the body represented is accelerating. Let's now discuss our third graph. This is the kind of graph that we have, a straight line, and this is a graph whereby it shows a straight line sloping from top left to bottom right. So one thing that we can see clearly is that this velocity is not constant but changing. How is it changing? It is decreasing, and since this is a straight line, we can say that the velocity is decreasing uniformly with time. This decrease in velocity uniformly with time is known as negative constant acceleration, and a better word to use is constant deceleration. Let's move on to graph 4. So we can see that this graph shows no longer a straight line but a curve, and in this case it's a smooth curve. What does it tell us about the body whose motion is represented here? It tells us that first of all, this is a non-constant velocity. The velocity is changing, but because this is a curve, this velocity is not changing uniformly but non-uniformly. So we can say that the velocity increases non-uniformly with time, and therefore this is increasing acceleration. The acceleration is also not constant but increasing with time. On to our fifth graph. We have this kind of a graph whereby this is a smooth curve. That's the first thing that we can see. Now this graph is different from what we had previously in number 4. We can see that the velocity here is not constant. The velocity is changing, and the change specifically is an increase. So the velocity is increasing but non-uniformly. So this is a non-constant velocity, and number 2, the velocity increases non-uniformly with time. This shows that the acceleration is decreasing. So the graph shows a decreasing acceleration. The next area of our discussion is to determine acceleration from a velocity time graph. We're going to base our discussion with an example, and we're going to draw first the graph, then show the labeling on the axis, that is time and velocity, on the x-axis and y-axis respectively. Then the next thing is to show the scale on both axes, then show the line. Now we now need to determine the acceleration of this graph, and the first thing to say is acceleration equals to the gradient of the graph. But how do we get the gradient? Gradient equals to rise over the run, or the change in y over the change in x-axis. This change in y-axis is simply the change in velocity, and the change in x-axis is basically the change in time. So what is the change in y, or what is the rise? Let us get the rise. We're going to show this line which is dotted. Our aim is to read the value on the y-axis, and this is 8. So to get the rise or the change in y, we take 8 minus this value which is 0. 8 minus 0 is 8. Therefore our rise is 8. Then we need to get the corresponding value for this point on the x-axis, and this point is 5. So if we take 5 minus 0, the run will be 5. So let us substitute the rise and the run this way. So we have 8 over 5, which simplifies to 1.6, and the unit is supposed to be meters per square second, since this is acceleration. So the basic point to take home is that for us to get acceleration from a velocity time graph, we need to determine the gradient. The steeper the line, the larger the acceleration. For example, having this graph whereby this is showing object A, and the second graph showing a graph for object B, we can clearly see or say that object A accelerates faster than object B, or object A has a larger acceleration than object B. Let's now determine the distance from a velocity time graph. Again, we are going to use an example, and our example is a graph whereby we have a velocity on the y-axis and time on the x-axis. Then the scale must be shown. That is the line. For us to get the distance from this graph, we simply need to take the average velocity multiplied by time. Average velocity is the sum of the initial velocity u and the final velocity v divided by 2. Then we multiply by the time so that we get distance. So what is our initial velocity and what is our final velocity? Our final velocity is 8 and our initial velocity is supposed to be 0. Then the time is 5. So let us substitute those values in our formula. We have just said that u, which is our initial velocity, is 0, v, final velocity, is 8, and time is 5. So this is what we have, and this simplifies to 4 times 5, which gives us 20, and the unit is meters, since that is distance. Alternatively, distance equals to area under the graph. So the area under the graph is simply this one here. We can see that this is a triangle, and for us to get the area of a triangle, this equals to a half multiplied by base multiplied by height. Our base is time, and this is from 0 all the way to 5. So that is 5, and our height is from 0 to 8. From 0 to 8, so that means height is 8. Now we substitute that information here. That is a half times base, which is 5, times 8, which is our height, and this gives us 20. Remember, the unit is meters. So we can see the two methods are the same. Getting the average velocity times time or area under the graph, they give us the same thing. We now need to discuss a more detailed question. Study the diagram below and answer the questions that follow. This is the diagram. It's a velocity time graph, whereby this is the graph we have. The first question, what is the initial velocity? To get the initial velocity, we need to read the velocity for which the time is 0, because when time is 0, that's when the journey begins. So time being 0 is at this point, and we can clearly see that the corresponding velocity is also 0. Therefore, initial velocity is 0 meters per second. Our second question, state the maximum velocity reached. To get the maximum velocity, we need to see or determine the highest point of this graph. And the highest point of this graph is point B or point C, for which the velocity is 40. So maximum velocity equals to 40 meters per second. Question 3. Calculate the acceleration in the first 20 seconds. Acceleration is simply equal to gradient, and gradient equals to the rise over the run, or the change in y over the change in x. So what is the rise and what is the run? The rise is simply from this point to this point, that is from point A to point B, and we can see that this is 40 meters per second. What about the run or the change in x? The change in x is simply from 0 to 20, and this gives us 20 seconds. Therefore, we substitute the rise with 40 and the run with 20, and our value simplifies to 2. Then the unit is meters per square second. That is the acceleration in the first 20 seconds. Now the next question is question 4, whereby we are required to explain what is happening between point A and B. So let us identify the 2 points. Point A is here and point B is here. Clearly we can see that the velocity at point A is 0 meters per second, or the object represented is at rest. Then the velocity at B is 40 meters per second. So the velocity is changing with time between point A and B. So we write that the object accelerates uniformly from rest, or from 0 meters per second to 40 meters per second. Question 5. Calculate the deceleration in the last 20 seconds. The last 20 seconds is from 50 seconds to 70 seconds. And to get the deceleration, we need to first get the acceleration. And we know that acceleration equals to the gradient. And to get the gradient, we get the rise divided by the run, or the change in y over the change in x. So how do we get the rise? The rise is simply from this point to this point, whereby we get 0 minus 40, which gives us negative 40 meters per second. What about the run or the change in x? This is simply 70 minus 50, which gives us 20. So we need to substitute for the rise and the run, like this. So the rise is negative 40 and the run is 20. If we divide this, it simplifies to negative 2 meters per square second. This is our acceleration. So to get the deceleration, we simply drop the negative sign, or multiply by negative 1, which gives us deceleration being equal to positive 2 meters per square second. The next question is question 6, whereby we are required to calculate the total distance covered during the whole journey. To get the distance covered, we simply determine the area under the graph, and this area under the graph is simply the area of a trapezium, because we can see that this figure forms a trapezium. Area of a trapezium is given by a half h into a plus b, whereby h is the height, a plus b, this is the sum of parallel sides. So what is h? H is determined from this point, and that is 40. Then a is from 0 to 70, and this is 70. Then for us to get b, which is this length, we need to get the difference between this point and this point. That is 50 minus 20, giving us 30. So H is 40, A is 70, and B is 30. Let us now substitute here. This is a half times 40 into 70 plus 30, which simplifies to 2000, and the unit is meters since this area represents distance. So our distance, or the total distance covered during the whole journey, is 2000 meters. We can also break this figure into three parts. That is this triangle, this rectangle, and this triangle. Then we determine the area of each of the figures, that is area of this triangle, the area of this rectangle, and the area of this triangle. Then we sum them together to give us the total area, which is the total distance covered. You can try this and confirm whether the answer you get is 2000 meters. Now we have come to the end of our lesson. Thank you so much. Thank you, and I hope to meet you in the next lesson. Goodbye.